The first time you sat in a window seat and the plane pushed back from the gate, you probably never noticed the small metal plate embedded at the base of the tail. It's about the size of a paperback book, painted the same shade of white as the fuselage, and it carries a sequence of letters and numbers that looks like random administrative clutter. But that plate is not administrative. That plate is the single most important identifier on the entire aircraft, and the code it carries is not random. Buried inside that string of characters is a complete engineering biography. The manufacturer, the model variant, the engine type, the production batch, the exact compliance status with every airworthiness directive ever issued for that airframe. Airlines don't talk about this plate because it exposes something they'd rather keep quiet. The code tells you which planes in their fleet have the original wiring, which ones have been re-engined with a different manufacturer's turbines, and which ones are operating on grandfather clause regulatory exemptions that no longer apply to new production models. You've looked at that tail 100 times. You never knew you were reading a dossier. The plate is formally called the Federal Aviation Administration Identification Data Plate, but within maintenance circles, it's known simply as the tail number tag. It's required by international treaty under the Chicago Convention of 1944, and every signatory nation must issue a unique alphanumeric combination that ties the airframe to a specific country's registry. When you see N8177 Alpha Bravo on a United Airlines tail, that leading N tells you the plane is registered in the United States. AC tells you Canada. AD tells you Germany. The letters that follow are not random. They are assigned in sequential blocks by the National Aviation Authority, and the sequence reveals the age of the registration. Eddie Rickenbacker, the World War I ace who later ran Eastern Airlines, understood this system intimately. In 1938, he personally lobbied the Civil Aeronautics Authority to reserve a block of numbers for the DC-3 fleet he was ordering. He knew that the tail number was the first piece of evidence investigators would scan if one of his planes ever went down. The historical secret here is that tail numbers were never designed for passengers. They were designed for crash investigators. Every plate is forged from stainless steel or anodized aluminum because it must survive a post-impact fire intact. The temperature tolerance is rated to 1,100 degrees Fahrenheit. Hot enough to melt the aluminum skin of the fuselage, but not enough to destroy the number stamped into that plate. The disruption comes when you realize that the tail number plate is actually the most visible part of a much larger hidden system, because the plate itself is just the front door. Behind it, etched into the internal structure of the tail, is a second code that the airline industry doesn't want you to know exists. In 1968, following the mid-air breakup of a Braniff International Airways Lockheed Electra over Nebraska, the NTSB discovered that the aircraft's tail had no serial number traceability after the fire. The investigators could match the tail number plate to the registration, but the vertical stabilizer itself had no permanent identification. They could not prove which factory had produced that specific tail section. The ruling that followed, Federal Aviation Regulation Part 45.13, mandated that every major structural component of a transport category aircraft must carry its own permanent identification, a second set of numbers that lives inside the metal itself, invisible to the passenger, but visible to anyone who knows where to look. Here's what the regulation actually requires: the horizontal stabilizer, both wings, the vertical stabilizer, the main gear beam, and the pressure bulkhead at the rear of the cabin must all be stamped with a part number and a serial number. These stamps are located in specific, documented locations inside the structure. And here's the part that airlines dislike. The internal stamps cannot be painted over. If an airline repaints a tail section, the ground crew must mask around the stamp and leave it exposed. The stamp must be readable from within 3 feet of the structure, without removing any panels. This means that during a routine heavy maintenance inspection, any mechanic can walk into the tail cone, shine a flashlight at the rear pressure bulkhead, and read the original serial number of that component. What the airlines know, and what they don't publicize, is that these internal stamps create a permanent audit trail. If a vertical stabilizer is damaged during a ground incident and replaced, the replacement part carries its own serial number. That serial number must be cross-referenced to the original aircraft registration in the maintenance logbook. The FAA database tracks every one of these swaps. A 2015 audit of a major U.S. carrier revealed that 7 aircraft in its fleet were flying with tail sections whose serial numbers did not match the original factory documentation. The discrepancy was discovered through a routine inspection of the internal stamp. The airline was fined $420,000 and required to ground the aircraft until the chain of custody for each tail section was fully documented. If you've ever stood at the gate and watched the tail of a parked 737 rise against the terminal window, you are looking at a component that carries more regulatory baggage than the cockpit. The vertical stabilizer is not just a piece of structure. It is a documented object with its own birth certificate, its own maintenance history, and its own chain of ownership. And here's where the system nearly bankrupted Airbus. In 2005, the European Aviation Safety Agency discovered that a batch of A300 vertical stabilizers, manufactured by an outside supplier, had not been stamped with permanent serial numbers. The supplier had used laser-etched markings that faded after repeated exposure to hydraulic fluid and de-icing chemicals. The manufacturer argued that the laser-etched numbers were compliant because they could be read with a magnifying glass within the first year of service. European regulators disagreed. The ruling forced Airbus to retrofit over 400 tail sections with replacement stamped plates, at a cost of approximately €800,000 per aircraft. Stay with me here, because this gets deeper. The cost of that retroactive program triggered the largest single liability claim in European aerospace history. The supplier went bankrupt within 18 months. The design requirement that emerged from that bankruptcy is the reason every A300 and A320 tail section now carries 2 redundant identification systems, one visible stamp and one radio frequency identification chip embedded inside the composite material. Now comes the escalation. The tail number plate, the internal stamps, the RFID chip. All of these are what the aviation industry calls passive identification. They hold information, but they do not transmit it. The active identification system, the one that broadcasts the tail number automatically every time the plane moves, is the one you've been interacting with without knowing. It's called the aircraft transponder. Every time you board a plane and the ground crew connects the tug, the transponder begins broadcasting a 24-bit code that is algorithmically linked to the tail number. Air traffic control reads that code automatically. The code tells them the aircraft's identity, its altitude, its speed, and its intent. But the transponder code is not the tail number itself. It is a cipher that maps to the tail number in a centralized database. That database, maintained jointly by ICAO and the national aviation authorities, contains the complete history of every registration change the aircraft has ever undergone. This is where the system gets interesting for the passenger who wants to understand what airlines don't advertise. When an aircraft changes ownership between countries, the tail number changes. A plane that flew as N8177 Alpha Bravo for a U.S. carrier might be re-registered as G Echo Bravo November Kilo when it moves to a British operator. The transponder code changes. The internal stamps do not. The internal stamp is the only identifier that follows the aircraft for its entire life. The tail number plate can be replaced. The transponder code can be reassigned. The stamp inside the metal cannot be changed without physically destroying the component. This creates a permanent forensic link between the airframe and its history. In 2019, a Boeing 777 operating for a South American carrier was found to have a vertical stabilizer that had been originally installed on a different airframe, a freighter that had been written off after a cargo fire in 2011. The tail number on the passenger aircraft said it was a 2006 build. The internal stamp on the stabilizer said it was manufactured in 2004. The airline claimed the stabilizer was a serviceable used part that had been inspected and approved for installation. The internal stamp proved that the component had survived a fire event that should have resulted in its retirement. The NTSB issued an urgent airworthiness directive grounding all aircraft operated by that carrier until every major structural component could be verified against its original serial number. And here's why this matters when you're at 30,000 feet. The engineering assumption behind the identification system is that every major component can be traced back to its original manufacturing batch, its original heat treatment record, and its original fatigue test data. When that traceability chain is broken, the safety margin calculations that certified the aircraft become meaningless. The transponder that sits behind the cockpit is broadcasting the tail number right now. The controller on the ground is reading that number against the database. But the database only knows what the airline reports. If an airline fails to report a major structural swap, the computer system has no way to know that the vertical stabilizer on that 777 came from a different airframe. This is the hidden system that the tail number plate really represents. It's not just a name tag. It's the visible edge of a global inventory tracking architecture that exists to ensure that every piece of every plane can be accounted for at all times. And the failure of that architecture is what regulators fear most. In 2017, an internal audit of the FAA registry database found that over 12% of active aircraft had at least one major structural component whose serial number did not match the registered airframe. The audit covered only U.S. registered aircraft. The global number is estimated to be significantly higher. The airlines don't want you to know this because the knowledge changes the way you perceive safety. You board a plane believing that the aircraft is a single, cohesive machine that was built in one factory and has remained intact since delivery. The truth is that every plane flying today is an assembled collection of parts from different production batches, different years, and often different manufacturers. The double-decker A380 carries a tail number plate that is physically larger than standard, roughly the size and shape of a smartphone. The plates on earlier A300 models are smaller and more deeply stamped because they were forged before the industry adopted laser marking as a primary identification method. The tail number on a Boeing 747 is located on the right side of the vertical stabilizer, approximately 1/3 of the way up from the base. On a 737, the plate is lower, closer to the hinge line where the stabilizer meets the tail cone. If you know where to look, You can trace the manufacturing evolution of the entire commercial fleet just by observing the location and size of these plates. The early models used raised lettering, stamped into bare aluminum. The newer models use engraved lettering on anodized surfaces that resist corrosion better, but are harder to read in low light. The A220 and the Boeing 787 both use composite tail sections. The identification plates on composite structures are bonded, not riveted, because drilling holes into the carbon fiber layers would create stress concentrations that could propagate fatigue cracks over the 20,000 cycle design life of the component. The design of the plate attachment was itself a subject of formal investigation after a 1991 incident involving a Boeing 747 operated by a European carrier. The plate detached from the tail during flight, struck the horizontal stabilizer, and damaged the elevator control rod. The aircraft landed safely, but the incident triggered a rewrite of the regulations governing how identification plates must be attached to tail structures. The current standard calls for a minimum of 4 attachment points. The rivets must be of the same material specification as the plate itself to prevent galvanic corrosion. The plate must be removable only with tools, not by hand, to prevent tampering, and the plate must be located within reach of a mechanic standing on the ground, without requiring a ladder or a maintenance platform. These specifications sound like bureaucratic minutiae. They are not. Each one came from a specific incident where the plate failed in a way that compromised safety. The FAA document that governs plate attachment runs to 41 pages. It includes diagrams of approved rivet patterns, tables of torque specifications, and a flowchart for determining whether a plate can be repaired or must be replaced if damaged during maintenance. The modern paradox is that the identification system has become so comprehensive that it creates its own failure mode. With 3 independent identification layers, the visible plate, the internal stamps, and the RFID chip, there are now 3 separate databases that must all agree. Discrepancies between the databases have become the leading cause of regulatory groundings. In 2023, a major European low-cost carrier was fined €3.2 million after a spot inspection revealed that the RFID chip in the tail of a 9-year-old A320 was transmitting a serial number that did not match the serial number stamped into the internal structure. The chip had been replaced during a repair without being reprogrammed to reflect the original component's identity. The airline argued that the chip replacement was a routine maintenance task and that the discrepancy was administrative. The European regulator ruled that the discrepancy proved the maintenance records were incomplete and ordered a fleet-wide audit. The audit found similar discrepancies on 11 additional aircraft. This is the system you are a part of every time you fly. You cannot see the internal stamps. You cannot read the RFIDs. But the plane you are sitting in is broadcasting its identity in 3 different formats simultaneously, and if all 3 do not agree with the central database, the aircraft can be grounded within hours. The next time you board a flight, walk past the tail and look for the plate. It's small, quiet, painted the same white as the rest of the aircraft. But that plate connects to a global infrastructure of databases, regulations, and inspections that spans every country that operates a commercial aircraft. The vertical stabilizer above that plate carries a serial number that you will never see. The RFID embedded in the composite skin is broadcasting a code that you will never hear, and the transponder in the cockpit is sending the entire package to air traffic control every time the aircraft moves. Airlines don't advertise this because the system only looks impressive when it works perfectly and catastrophic when it fails. The failure rate is extremely low. The consequences of a failure are what drive the regulations. You now know where to look, and you know what that code means. The next time you see a tail number, you are not just reading an administrative label. You are reading the fingerprint of a machine that has been tracked, logged, and audited since the day it was built. And you are one of the few passengers who understands what that fingerprint actually contains. When you settle into your seat and glance out the window during pushback, that tail number is the first thing the ground crew verifies before the tug connects. They shine a flashlight on that plate and call it into the tower, confirming the aircraft identity matches the flight plan they filed hours earlier. You sit there scrolling through your phone, unaware that the entire departure sequence is conditioned on a 3-second visual check of a metal tag the size of your palm. The system works because it is built on redundancy that the passenger never sees. The tower cross-checks the transponder code against the flight plan. The maintenance logbook cross-checks the internal stamp against the component history. The RFID chip cross-checks itself against the central database every time the aircraft powers up. 3 independent verification layers, each one capable of grounding the aircraft if the others disagree. But there is one final layer that no regulation mandates and no database tracks. It is the layer that every experienced mechanic uses as a gut check, and it is the reason the tail number plate is never painted over completely. The plate catches light differently than the surrounding fuselage skin because it is made from a different alloy. In certain angles, especially during the golden hour just before sunset, that plate reflects amber light in a way that the rest of the tail cannot. Ground crews call this the whiskey echo reflection, a visual cue that tells them the plate is still there, still readable, still attached with all 4 rivets. If the reflection looks wrong, they stop the pushback and call for an inspection. They have no formal training for this. They just notice, because they have been doing the job long enough to know that small things matter more than big ones. This is the secret that the identification system was designed to enforce but cannot guarantee. The human eye remains the final verification layer. The databases can be corrupted, the stamps can fade, the RFIDs can be misprogrammed, but a mechanic standing on the tarmac, looking at a tail number plate in low light, can see in one glance whether the system has been compromised. The vertical stabilizer above that plate carries the weight of every regulatory decision, every maintenance log entry, every audit finding, and every accident investigation report that has shaped the modern aviation industry. And the plate itself, that silent witness bolted to the tail, is the only part of the system that remains exposed to the elements, readable by anyone who walks past it. You will never see the internal stamps inside the tail cone. You will never hear the transponder code being broadcast, but you will see that plate every time you board a flight. And now you know exactly what it contains. That is the quiet superiority that this knowledge gives you. The certainty that the most important piece of information about any aircraft is right there in plain sight, waiting for someone who knows how to read it.